Okay, so now we're going to move on to the next material, and that's chemical kinetics, chapter 13 in your book. I guess the plan for this is 2 weeks. There'll be 5 videos that I put out. Each one will probably hopefully about a half hour or so long. Try to break it up a little bit better this time. So let's get into this. All right. Kinetics. What kinetics is the study of factors that govern basically how fast reactions take place and how reactants change in the products. So speed and how quickly reactants disappear and products form. Okay, kinetics is used a lot. Okay, they use it in pharmaceuticals whenever they look into enzymes and drugs, how to make drugs and make and having drugs. How well drugs work is based on kinetics, how fast and how well they can bind to the enzymes and proteins. Uh, and it's basically, when we talk about chemistry so far, really we talk about a beginning and end product, but kinetics is going to talk about the path on getting to from beginning to end. So part of this is that we will do a little bit of this, is that you can actually look at the individual steps going from your reactant to your product. Okay, it's not just boom and it takes place. Okay, it's not a magic. It actually goes through steps, and as a reactant goes to product. And during kinetics also looks at how the reactant turns into a product. So it looks at how R changes into P, and R might change into an intermediate. Okay, and then that might change into another intermediate, and then finally into your product. Okay, and that's what kinetics looks at. And I really like kinetics because of that. It shows what's going on. Not only what's going on, but how fast and other variables along the path. Okay, so there are factors that affect chemical reactions. The first one is the chemical nature of the reactants. What the elements, maybe like their electronegativity, maybe the polarity, the charge involved, what kinds of bonds, if you have a strong covalent bond, a weak covalent bond, and so forth. And these relate to the activity based on their fundamental differences. Okay, another key thing that affects chemical rates besides the chemical sort of makeup is how well the reactants can come together. So if you have A plus B going to C, how well do A and B interact with each other? Okay, and they may be very specific on how they interact. A might look like this, and B might look like this, and so there's a really specific orientation that A has to work. So if A comes in like this, the reaction isn't going to take place, and so the reactants may have very specific ways that they interact. And if you ever get into biochemistry, you'll talk more about enzymes and how they work. Gases in solution really facilitate because you have a homogeneous mixture where things are moving around randomly and they'll hit each other a lot easier. Diffusion, which is a random event. Okay, like when you drop food coloring into water, it diffuses. We call that, and that is the quickest way of how things can interact without having something force the connections. Okay. Right. Heterogeneous actually don't do very well. But they could, because if you have a solid and like sand and water, okay, down here is the sand, and then you mix it with something else that's also solid. Those two solids may mix together really well and form a homogeneous mixture. Okay, another thing is how much of the reactants you have. The more reactants you have, uh, the faster the chemical reaction will take place, and that's just quality of mass. Okay, mass interactions. There'll be more likely A's bump into B's. Okay. Right. Temperature is also another factor. If you increase the temperature, you increase the speed, which increases more likelihood of particles to run into each other. Right. The other one is the additive quality, and that's the presence of a catalyst. Catalyst is a substance you add to a chemical reaction. What happens is the chemicals that participate in the mechanism, but are regenerated in the end. So when you put a catalyst into a chemical reaction, like A going to B, then you add a catalyst. Okay, what the catalyst do is it's gonna make this reaction take place faster, but the catalyst is basically gonna be unchanged. Okay, so it's you don't really count it as part of the reaction. So it would be catalyst plus A gives me B plus catalyst. All right, so no change happens to the catalyst. And enzymes, if you take biochemistry, are a biological catalyst. Okay, so if you want to, we're interested first of all how fast a chemical reaction takes place, maybe A going to B, and that's called rate. And rate can be measured different ways, like getting paid. I get $10 per hour. In terms of chemical reaction, rate of chemical reaction is measured as the reaction rate, and it's the change in reactant over the change in time. Okay. Now, you could have it the other way. You could have measure product B, so you could write it the reaction rate of change of A over change in time, or you could actually measure B as well. It doesn't matter. Okay. This is what you'll notice is that if you do it in terms of A, you get less and less of A, and if you do in terms of B or product, you get more. All right, so let's see how this writes out. So you can write, let's say we have a reaction X going to Y. All right. Okay, so you would say the rate of X, all right, would be the initial time, and then your final time. So it's always final minus initial. That would be the change in X, how much X has changed, and T, final time minus T time, which delta T. And then you're going to have these units here: moles per liter per second, moles per liter seconds, or molar per second. Or I've also you'll often see this maybe writing as moles liters minus 1, seconds minus 1, or even molar seconds 1. Okay, minus 1. The other thing to keep in mind here is that the brackets represent concentration. So we might say product increases by 0.5 moles per liter. So that's why brackets mean concentration. And here's the concentration right here. Okay, so when we write the rate of reaction, it's always got to be positive. So you're always going to be, so the as you get rid of x, x is going to go down. So it's going to be a negative, so you put a minus. So if you measure the rate in terms of reactant, you need to put a minus in front. If you do it in terms of the product, because it's increasing, you don't have to put change the sign. So both of these are always positive. Okay, now rates and coefficients. Okay, so let's look at chemical reactions. This is propane being combusted. Now, for every time this chemical reaction takes place, you'll make one of these, 5 of these, 3 of these, 4 of these. Now, if we compare, if we say one reaction, and it's changed per time, okay. All right, how to do each one of the substances? How can you write this in terms of each one of these? Okay, so if we write this reaction, so if we know the speed of this reaction here, okay, the overall reaction, okay, because of coefficient 1 here, that means for every one reaction, you'll lose one of these. Okay. All right, for every one of reaction of these, okay, you'll actually make 5. But if we want to compare those 5 to one of these, we have to divide it by 5. So if we measure the amount of oxygen given off the reaction, we'd have to divide it by 5 to get the same as this. So let's say you make 20 oxygens per second. Okay, that's going to be the same as doing only 4 reactions. All right, so whatever value you get for the speed of oxygen, you have to divide it by 5 to relate it to the original. Same thing with the carbon dioxide. All right, let's say you measure, there's 18 per second of carbon dioxide being formed. Okay, well, to find out how many reactions that are taking place during that time, you divide that by 3, and you get 6. Okay, so hopefully you see how that works. So if you want to find out, so what these numbers are here, they're telling you how many how many reactions you can find by measuring each one of the components. So if you had 40, if you measure 40 waters, that's not going to be 4 per second, okay? Right, that's not going to be how many reactions take place. Because for every reaction, you make 4 waters. So you have to divide this by 4, or multiply by 1/4 to get how many reactions. So this would be 10 reactions. Okay, so this shows the relationship. So for every oxygen, so there's, for every oxygen you make, every oxygen, you're going to make 5 times as many oxygens as you are the propane. So what you have to do is, if you want to make these rates equally, you have to multiply the amount of propane by 5. And so forth, okay? Okay, so let's say you have a chemical reaction right here, and you want to come up with a rate, okay? You may say to yourself, well, which one should I measure? It really doesn't matter which one you measure, as long as you know the relationship between each one. It's always better to measure the easiest one. So let's say you make, C is the easiest one to measure. Then measure the rate in terms of C, and then if you need to figure it out in terms of the rest of the reaction, you can just divide by its coefficient. So let's say these coefficients are 1, 2, 3, and 4. Okay. And you do the chemical reaction, and you measure how much C is formed. To relate it to hold the reaction, you would divide it by 3. So the rate of the reaction would equal to 1/3 the speed of C. All right. Let's do one. Let's just do an example. Okay, so here's the chemical reaction, and what we want to do is write the rate of the reaction in terms of the NO. But we want to relate it to the whole reaction. So for every one reaction, make 2. So the rate is going to be half this value. The other thing is that we're measuring the reactant, so it's going to be a negative value because it's going to decrease. And so we look this. So this guy is 1/2, so it's exactly what we want. It's negative, and so this is the correct one. All right, the next one, based on the reaction. Okay, again, this is one reaction, and the reaction of CO2 is 2 molar per second. What would be the rate of the oxygen? Okay, so for every CO, we're going to make, for every 2 COs, we make 1 O2. So the amount of O2 is going to be half of what the CO is going to be. So it's going to be this guy. Okay, generally, change the reaction rate with time. Generally, reaction rate changes during reactions. They change during the reaction. They're not constant, and we'll see why. All right. So it's not linear. Okay, so it doesn't go. So the amount of reactant doesn't go down straight like this. Usually, what happens is it starts out fast and then slows down. And that's basically because there's less and less particles to bump into each other, and so the reaction doesn't take place. It's often initially fast, and then it slows down. And that's because the reactant depletes. You have less and less of it. And there's less and less particles bump into each other, and so it slows down. So if there was an infinite number of particles, it would be linear, okay? But as particles go, maybe start out with 50 at the beginning. After 5 minutes, you might have only 20 left, and then these guys will be harder to find each other, and so they're going to slow down. The chemical reaction can slow down. So the reaction is dependent on the concentration. Right. How do we measure rates? Well, we have 3 ways to do it. One is you can measure instantaneously. You take a measure immediately at any given point. Another way to do it is you measure how much you start out with, how much you end over a certain time, come with the average. And then another way to do it is measure right at the beginning of the reaction when you have all the reactant available. Okay, instantaneous reaction rates. This is calculus. If you've had it before, what you do is you just measure. So that usually the reaction is a curved line like this here. Okay, so it's curved, and it's curved. What you can do is you can measure any point on there when what its rate is, and you can use calculus to do that. All right. The initial rate is you measure right at the beginning. Like I said, as soon as you click, as soon as you turn this thing on, you measure its rate. And then the average rate is you measure 2 points, both their beginning and end points, and also their times, and then just do a simple average. Okay. Now this will have some problems since we're assuming in this case that it's a linear relationship, when in reality it's going to be a curve relationship. But this isn't a bad way to get some good approximations. Okay, concentration versus time. So what we have here, this is our graph. Rate at any time equals the negative slope or tangent line of the curve at any point. So this is where we'd use instantaneous. So the rate is the minus slope, and you can do it instantaneously, and this is where you might want to use calculus, or you could do it simply if you were going to do rise over run. Okay. So you could take any point here, beginning point, end point, do average or instantaneous using these methods, this method. Okay, so here's one just using the average method. So here's your beginning, your initial concentration. Here's your final concentration, and here's the times. And so what you do is you take your final concentration, subtract your initial concentration over your final time, initial time. All this molar error and per second, and do simple math. Remember, this is a minus sign because we're measuring reactant. Have to put a minus out front, and your value is 5.68 times 10 to the minus 4 molar per second. Okay, so just another way, again, similar type of thing. You just get 2 points, and then you're using a tangent here. So this is like using calculus. If you're using calculus, you'd use an infinitesimally small tangent, but we decided to use some tangent that goes through each line. You find out 2 points on that tangent, both their concentration and their time, and then subtract them and come up with these answers here. Okay, so let's look back at the previous problem. Previous problem we took 2 early points, and then here we're going to do the same thing but take 2 later points and see what the rate is. If we do that, we do the same way, but what we find here is the rate is slower. Okay. So the rate is dependent on, when you do it and how much you have. Now, using this example, we'll see that there's other examples as well. But when you do rate of reactions, you have to be careful and make sure you specify what you're taking the rate of and when you're. Okay, so this is the last problem of this slide. So what we have is reaction, and we measure how much you start out at 5 minutes. You have 0.0258 at 5 minutes. After 10 minutes, you have 0.097. So you have your final over minus your initial. Subtract your final minus your initial. There should be a minus sign out front of here. And then 2 minuses because this is a minus, so you put a minus sign out front here. And then that rate is going to be 3.2 times 10 to the minus third molars per minute. Okay, so this is introductory to kinetics, and the next slide will be more specific. Talk about how do we apply it.